you go to Piazza, there's some kind of glitch in it, and it's bringing up my old class from the summer. And so the best way to sign up for Piazza is using the link I emailed out. If you're trying to add the class, you wouldn't have gotten the link, but you can talk to me about getting the link. I can send it to you. And so that's Piazza. How about Newton? Are you guys starting? I know one person this morning said he finished all the problems and he mastered for chapter 1, and so he's just once you hit mastery, you can still continue. There's additional problems that they have. There's actually quite a few problems there, so he said that's what he's doing, is he's going through extra problems. But in addition, I'll make an announcement in the morning class. You can also do these end of chapter problems here. In the end of chapter problems, the ones marked in blue have the answers there. And so that's always helpful to have the answers. You can check your work immediately. But not only can you check your work immediately, it allows you to go through these problems quite quickly, because if you can't come up with the answer within a reasonable amount of time, then I just look at the answer. This is just for additional practice. One of the things that happened when I was a student at UCLA is the student next to me was setting the high score on the test, and I was wondering, how is that student doing that? And so I got to be friends, and I found out that what they like to do is they like to do every single problem at the end of the chapter. And I thought, every single problem, how do you have time for that? Because some of the times the problems take me like 30 minutes, an hour, 2 hours, and I'm still haven't finished. And the situation at UCLA is they give not just the partial solutions guide. This would be the partial with the blue. They give the complete solutions guide. And so the way that they did it was they just, if they got stuck, they just read the answer. So I started doing it too. And I went through every single problem in the end of the chapter. When you go through every single problem at the end of the chapter, if you get stuck, you don't want to waste too much time. You read the answer, and then you get a lot of experience. And that experience makes a lot of difference. Somebody who has a lot of experience versus somebody who has very little experience in terms of problem solving. The person with a lot of experience is going to be able to solve a lot more problems. That's for sure. It's like a mechanic. Somebody who's only changed the oil, and now all of a sudden you expect them to rebuild the engine. Well, that's a whole different thing. But here you can get a lot of experience in a short period of time by doing it this way. And so that's something I would recommend doing, especially this person who has extra time, that's what I'd recommend to that person to do. Let's continue on here. The other issue that came up was this, the title of the book. Now I figured out what had happened. Let me turn this off. What had happened was this. My book is the Introductory Chemistry, and it's bound. And since it's bound, this is a book you could sell back to the bookstore. But our book that we're using right now is loose, not bound. They don't accept returns, or they don't accept to buy back any unbound books. Well, that's a disadvantage, but the advantage is if you don't have it bound, then it's a lot cheaper. So it's just one of those cost versus benefits. But Introductory Chemistry or Beginning Chemistry, it's the same book. Just one is bound, the other's not. Okay. And they don't want people to sell this book back as Introductory Chemistry if it's not bound. And so there was that issue. Then the final thing was with Newton. Some people were having trouble getting Newton at the discounted price, and I'm not sure if they have it figured out yet. So what I would recommend is just go ahead and get started on Newton without the code.
I went to the bookstore yesterday, and they're still waiting for all our names to get in. That's why we think there's a discount at the bookstore.
Oh, okay.
But I like the 14-day trial.
It's Yeah,
that's all it is.
Yeah, 14-day trial. Do that, or waiting for financial aid. That's the best thing to do. And once they get it figured out at the bookstore, then that's okay. I sent them the list for this class, but there are 4 classes during this semester. Okay, I think that was it. Was there anything I missed? People had questions about? No. So we're going to continue. We're talking about matter. What do chemists study? Chemists study matter, the physical material of the universe. And so what's the first thing you notice about a piece of matter, like this, or whatever else, what other piece? When you're thinking about matter, matter comes in all kinds of shapes, sizes, forms, whatever. And so when we're thinking about matter, probably one of the first things we notice is what the state of matter is. And so the states of matter. The states of matter are solid, liquid, gas. There's actually a fourth state of matter. Does anybody know the fourth state of matter? Plasma. Plasma is actually the most abundant state, or the most prevalent state in the universe, but on Earth it isn't. So, like the lamps here, the fluorescent lamps are inside the tubes of plasma when they're operating. The sun is a plasma, a different kind of plasma. The sun's plasma is called a thermal plasma. These are non-thermal plasmas, non-equilibrium plasma. But plasmas, we may talk about that a little bit later. That would be it. But solids will. You can easily recognize a solid, right, versus a liquid versus a gas. I mean, pretty much doesn't require much explanation, I think, because you're already familiar. But let's put some definitions on the solid. A solid's going to have a fixed shape and volume. It's a fixed shape and volume. Solids are made up of atoms, like everything else. Made up of atoms. So how are the atoms arranged in a solid? Well, we saw, the atoms are going to be, or it doesn't have to be atoms. It could also be molecules. In other words, what the book does is, they don't know if it's an atom or a molecule, so instead they use this word particle. And so a solid is going to consist of particles. So the particles are going to be either atoms or molecules. So for example, in gold, we'll have gold atoms, but in ice, we're going to have water molecules all put together. And those particles are going to be held together either strongly or weakly, For example, the particles in gold are held together quite strongly. In gold, how do we know? One, gold is, you can try to break the particles apart using a hammer, but you really aren't going to be that successful because what's going to happen is it's going to flatten out. The particles are still going to hold on to each other, right? Or what's another indication that the particles are held together very tightly, very strongly? Density. Well, the density doesn't always. Mercury is extremely dense, but particles are held together pretty strongly, but not as strong as a solid because mercury is a liquid. What's another indication that the particles are held together very, very strongly? Well, structure, I'll tell you, methane and gold have the exact same structure. When you look at the solid methane, so if you were to freeze methane, or solid argon, or solid krypton, all those have the same structure as gold, but it doesn't necessarily indicate how strongly the particles are held together. The structure is how the particles are arranged in three-dimensional space. That's typically what we think of as structure. Yeah, melting point and boiling points, exactly. Melting points and boiling points. Normally when I think about like temperature, like gold, let's say this is gold, the particles are held together very tightly. And so what we see in something like gold or any solid is there is no what we call translational motion. translational motion is taking this particle and moving it to a different position in space. And so the particles are pretty much stuck together, and they're stuck in one position, but they're not completely immobilized. There is mobility in that, and that is, there might not be translational motion, but there's other motion. Do you know what other motions there are? There are only 3 types of motion. One motion is translational, moving from point A to point B. Another type of motion is motion. Motion is often called kinetic. Kinetic is motion and energy, because you have to have energy in order to move. So it's kinetic energy. And so probably one of the most important types of kinetic energy or motion is translational kinetic energy or translational motion. And it's moving from point A to point B. Well, solids don't do that. Molecules are kind of fixed. Particles are fixed. Atoms are fixed. Another type of motion is what we call vibrational motion. And so even though in gold the particles are fixed in a position here, it doesn't mean they can't vibrate. They can vibrate. And in fact, at room temperature, they are vibrating. What you have to do is, if you cool it down, then the vibrations slow down. As you heat it up, the vibrations speed up. Basically, temperature, when we feel or sense temperature, we're sensing the motion. If we touch a hot object, that means the hot object, has a lot of kinetic energy, a lot of motion. And that motion is being transferred to your skin cells, which are going to create or cause them to move with rapid motion. And so these can vibrate. They're spherical, so another type of motion that we often see is rotational. So for example, in ice, the water molecules might be stuck in ice. There's 2 hydrogen and oxygen in the center. But is there enough room for the water molecule to rotate in ice? Do you think? Do the water molecules rotate in ice? No, actually they're kind of stuck. There's not enough room, and plus the way the attractions are held, they can't. But certainly they can vibrate. So water molecules in ice can vibrate. Gold atoms in gold can vibrate. And so this is what we see here. These can vibrate. The higher the temperature, the more intense the vibration. The lower the temperature, the lower the vibration. In fact, what you can do is you can keep lowering the temperature, and the golds vibrate slower and slower, and eventually you'll hit a temperature where the gold atoms stop vibrating. Do you know what temperature that is?
Absolute zero.
That's what we call absolute zero. Absolute zero is the coldest temperature you can achieve, because once you hit that temperature, there's no more motion. And temperature is just a measure of the motion, the kinetic energy in the sample. And so if we cool this to absolute zero, well, what is absolute zero? Absolute zero is about minus 450 Fahrenheit, or minus 273 Celsius, or what we call 0 Kelvin. Kelvin is the different type of temperature unit. It's the absolute temperature. Okay, there's no translational motion, but vibrational and rotational motion is okay. Water molecules can't rotate, but there are other types of molecules that can rotate in the solid phase, and spin and rotate, whatever else. Like methane. Methane would have no problem rotating in the solid phase. All right, and this is pretty much what retains its shape and its volume. Its volume. Can you squeeze gold into smaller volume? Is it possible to compress gold? Say, kind of compress it to a smaller volume, or expand it to a larger volume? Not really. Solids are not compressible. They're not compressible because there's no space. There's no room. You compress them together, the atoms are already touching. So, back there. So they're not compressible. Liquids. Let's take a look at liquid motion. Liquids have a fixed volume. They have a fixed volume. Liquid, because the particles still touch. You know, the particles are still being held together. And so in the liquid, you know, the particles are stuck together, and therefore they don't fly apart. However, the only difference is now we have translational motion. So even though they're stuck together, they can break free of one, but they're still going to be stuck to another one, or get stuck to a new one. You know. And so as long as they maintain that, they're okay. And so with a liquid, now we have translational motion in addition to the vibrational rotational motion. And so the volume is going to be fixed, because if you try to compress a liquid, there's no space. I mean, the particles are all still touching one another. Then, in other words, they're still held together in the liquid. Now, if you were to melt gold, what happens is, yet you break the bond that holds them together, but there's still the attraction between the atoms that will hold them together, but not as strongly. If you break, if you melt ice, then you're breaking what we call the intermolecular attraction, intermolecular force that held water molecules together in ice. So now we got translational motion. The volume is going to be fixed because, you know, still they're touching, but the shape is the shape is going to conform to the container, the shape of the container, and so the shape is variable depending on what the shape of the container is. So just fit to the shape of the container. There's going to be more disorder, you know, here. You know, when we see this, the solid could be nicely ordered like this, or the solid could be disordered. You know, if we have a nicely ordered solid like this, what do we call it? A crystalline lattice. If it's slightly disordered, but there's still no translational motion, if it's disordered with no translational motion, that it is solid, then we call it amorphous solid, or glassy solid. Over here, there's going to be disorder. In all liquids, there's going to be disorder, but now there's translational motion. And so some people liken amorphous solids to frozen liquids. You know, if you take this liquid, rapid freeze it, you got an amorphous solid. If you slow freeze it, you know, it gives the atoms or the molecules time to arrange themselves in a nice, orderly position, and it can crystallize. And so one of the ways that people make amorphous solids is rapid cooling. Try to quench it quickly. All right, that's the liquids. Then we go on to gases. For gases, we got the boiling point. Now the boiling point is going to get this. Okay, now we got, basically, as we heat this up, this is what's happening. As we heat it up, the vibrations get so intense, you know, it breaks the bonds, kind of, but they're still stuck together because the vibrations aren't that intense. Over here, when we're at the liquid and we go to the gas, then the vibrations get so intense, there's so much kinetic energy, you know, the higher temperatures, that these can break free. If those break free, then we have gas in which the particles are completely broken apart from each other. And in gases, we got mostly empty space here, in which the particles are free to translate, rotate, and vibrate. And so for gases, what we have is we have both variable volume, because variable volume means that they can be compressed or expanded. If you compress the gas here, you're just pushing the particles in closer together and reducing the amount of empty space. If you expand it, you're just pulling the particles apart a little bit more. And so gases can be compressed or expanded, unlike liquids and solids. Liquids and solids aren't really compressible. And then we have variable shape, of course. It's just going to fit the container. But in the case of a gas, it fits the entire container. In the case of a liquid, it just fit the bottom of the container, or however high up the liquid goes in the container itself. And so maybe we can show that here. But this would fill up the entire container. All right, so one of the first things we notice, And so the air in this room is a gas. This is a solid, and like this would be a liquid here. Okay, then what else would we notice about this thing? So the first thing we look at would be kind of the state. The next thing we probably notice about that piece of matter is this. Is it homogeneous in appearance or heterogeneous in appearance? And so when I look at this countertop looks pretty homogeneous in appearance. Homogeneous means it looks pretty uniform throughout. The whiteboard is pretty homogeneous. If you look at other things, like some matter would be like muddy water. Muddy water might be kind of heterogeneous in appearance, right? Those kind of things. So we look for homogeneous or heterogeneous. Sometimes, this will tell us if it's a mixture or pure. For example, if it's heterogeneous, then this is typically a mixture. If something doesn't look uniform, it's probably a mixture of different things. Typically a mixture. However, that could be deceptive, because sometimes it's heterogeneous and it turns out it's pure, and it could be due to color. Color sometimes is deceptive. Take salt, for example. If you look at table salt, color is table salt. Table salt looks white. But if you take one crystal of table salt and look at it closely, is it white? It's not white. It's colorless. It's totally transparent, clear. And so color can be deceptive, because table salt is actually colorless. No color. That white is just because of how light is scattered off the surface of the crystal. Now, the same thing happens. You could have pure silver, and it could look silver and it could look black. Tiny crystals of silver to your eye look black. If you look at those tiny crystals under a microscope, then they'll look silver. And so it could be heterogeneous in appearance and still be pure. That is, it could have silver and black, and it's just all 100% silver. And so you have to watch out for colors, because colors are very deceptive. This is why in geology, they try to get rid of the factor of crystal size. The bigger the crystals, they have slightly different colors than smaller crystals. And so geologists, they get a porcelain plate and scratch the sample on the porcelain plate to make a powder, and this powder, hopefully the particle sizes, particle being different. Particle, according to Kropalici, is an atom or molecule. To a geologist, a particle would be a tiny crystal. And so these tiny crystals, as long as they're consistent size, then you can compare the colors. But you don't want to compare big crystals with little crystals in terms of color, because you can be tricked. Well, anyway, if it's heterogeneous, something like sand and water, sand and water that's heterogeneous. That's going to be a mixture. It's a mixture of sand and water. Sand would be, quartz. Most beach sands mainly made of quartz. Sometimes there are other minerals in there as well. Now, if it's homogeneous, we don't know. Homogeneous, it could be a mixture, or it could be pure. When I say pure, I'm talking about a substance. What was the substance again? The substance has fixed composition or variable composition? Fixed composition. And so those fixed composition things would be could either be a element or a compound. And so if something's heterogeneous, it's likely to be a mixture rather than pure, you know. But if something's homogeneous, then it's kind of hard to tell. So this is homogeneous in appearance. It looks very uniform throughout. Therefore, can you conclude that this is pure water? 100% pure water? No. Because you can't tell just by looking at it, right? You can't tell that this is pure. This might be a mixture. There could be other things in here. And you already know that this is tap water. This is a mixture, right? But if you didn't know that this was tap water, how can you tell? How can you tell the difference between pure water and tap water, or pure water and contaminated water?
When you boil it, that was left.
When you boil it and see what's left?
Yeah.
Okay, what if I didn't want to boil it? Let's say you could taste it? Yeah? That's true. Normally we don't taste anything in lab because it might be dangerous. But you know, even though we don't taste it, we do smell things in lab. When you smell things, you don't hold it under your nose. Otherwise, you can be overwhelmed by the fumes. What you do is you just waft. You know, there's going to be some molecules maybe coming off the surface. You waft some molecules through your nose. That way you can detect it. So chemists will smell things sometimes. I don't know what, you know, maybe this smells like water. Maybe it's pure water. I don't have that sensitive of a nose, you know. Maybe those wine, the sommeliers, they can tell that's pure water. But anyway, how would you tell? Actually, I want to know, you know. I want to know this. Well, we got to think about that. For mixtures, what we want to do, you know, if we have a mixture, we want to know the composition. You know, we want to know the percent of substance A, the percent of substance B, etc. And so for mixtures, typically we could have some kind of mixture. Let's say muddy water. Muddy water is like 40% mud, 60% water. You know, mud being a mixture of different things in itself. And then we break down the mud. The mud consists of this much, you know, of this mineral, this much of that mineral. Minerals are substances. Rocks, you know, rocks are rocks substances or mixtures. It turns out rocks like granite, limestone. Well, actually, limestone may not be. The granite and lots of other rocks are mixtures of minerals. Minerals being pure substances.
Hemoglobin and blood, what is that?
Hemoglobin, okay, is a substance. Blood is a mixture. And so, you know, you're going to have a certain percentage of hemoglobin in blood, and we'd want to know that, you know, how much hemoglobin there is in blood. And so typically if we have a mixture, we want to know the composition because, you know, for example, if I have sugar water, although sugar water is going to be homogeneous, you know, if I have sugar water, I want to know, you know, how much sugar I have in there. That's going to dictate how sweet it is. And one thing about mixtures is the composition of a mixture is not fixed. The composition of mixture is variable, you know, variable depending on where it came from, the origin, whatever else. And so mixtures have variable composition, you see. And the properties are going to depend on, you know, what percentage sugar, what percentage alcohol, what percentage whatever is in that mixture. And so the higher the percent sugar, the sweeter the sugar water is going to be. And so that's what we need. And the same thing over here, you know, if we've got a mixture, we want to know the composition. And so let's do an example here. Air, you know, is air a substance or is air a mixture? Air is a mixture. And so if we have air, then we want to know what its composition is. Well, the air is going to vary. So for example, the air at the top of Mount Everest is going to have a slightly different composition than the air at sea level. And so let's take the air at sea level. The air at sea level is going to have, and this is just crude, but it's been analyzed a little bit better. Air is such an important mixture that they come up with some percentages for each of the components in air that are fairly accurate. But we don't need to do that. We're just going to get approximate. The approximate composition of air is it's going to be 20% oxygen. Now the oxygen in the air, is that O, O2 or O3?
O2.
O2. So it's 20% O2. It's a gas, so we can use this little G here to represent that. It's 20% O2. Now what does that mean? It means this, 20 out of 100 are O2. So 20 parts of O2 for every 100 parts of air.
This is based on volume, not mass.
Yeah, this is not based on mass. Or it might be, because I haven't defined the parts yet. And so I need to define the parts. When I'm talking about parts, yeah, right. It could be if I have 100 grams of air, I would have 20 grams of O2, but that's not how it works in this percentage. How it works in this percentage is either by volume or by molecules. This is the percentage by molecules, and so turns out to be the same as volume by, percentage by volume, because of a property of gases, which we'll talk about later. But anyway, I'm going to have 20 molecules of O2 for every 100 molecules of air. And so if I take 100 molecules of air, 20 of those should be O2. Then I'll have 80% N2 gas, which is just going to be 20 molecules, not 80, excuse me, not 20, 80 molecules of N2 for every 100 molecules of air. Well, air is not just a two-component mixture. I'm just assuming it's a two-component because these are just very rough. What else is in air?
Carbon dioxide.
Carbon dioxide. Now, the level of carbon dioxide is kind of low. It's a very small percentage. What else is in air? Ozone, carbon monoxide, oxides of nitrogen like nitric oxide, nitrogen dioxide, nitrous oxide.
Maybe mercury.
Maybe a little mercury vapor, especially around these parts because people break thermometers all the time in the lab. In fact, because of the problem of thermometers breaking all the time, it's hard to clean up the mercury. And so most of the thermometers you're going to be working with this semester are going to be alcohol thermometers, not mercury thermometers. But there could be a little bit of mercury, hopefully not much mercury. There could be a little bit of carbon monoxide in air. Carbon monoxide, this is why a lot of homes now are required to have carbon monoxide detectors. In fact, I think all homes are required to have carbon monoxide detectors now because of the carbon monoxide levels. In fact, the carbon monoxide levels dictated by OSHA, I think, are about 8 ppm, 8 or 10 ppm. You cannot have more than 8 ppm carbon monoxide in an 8-hour period in indoor air. Otherwise, you're exceeding the OSHA guideline. Well, what is a ppm? Well, ppm is another way of expressing the composition. And so what a ppm is this. You have to recognize that a percent is a p part per 100, or pph. And so a percent is a pph. So what is a ppm? A ppm would be something like this. And so let's say we had, let's say we were right at the limit. And so this is for, if we have higher, what we call concentrations or higher percentages, then percentages works very fine. But if we have very, very small percentages, then percentages aren't so convenient. And so sometimes we use something like a ppm. So let's go 8 ppm carbon monoxide. Carbon monoxide has 1 carbon, 1 oxygen. It's fixed composition. It's a 1-to-1 ratio. This is a molecular compound that occurs as small molecules of CO, carbon monoxide. It's also a gas. If we have 8 ppm carbon monoxide, a ppm is a part per million. And all these are kind of the same. And so if we have 80 parts per 100, this is 80 parts per 100. If we have 8 ppm, that's 8 parts per million. So we just do the same thing, 8 parts of carbon monoxide for every 1 million parts of air. And so what that means is this. That means is we didn't want to use percentage because percentage is kind of an inconvenient unit for carbon monoxide. And so if we did this in terms of a percentage, this is what we'd have to do. If we did this in terms of a percentage is a part per 100. We have a part per million. So what we do is we just move the decimal place over. 1, 2, 3, 4. We'd move it 4 over because that gives us 100 here. If we move it 4 over here, we'd have to move it 4 over up here. So 1, 2, 3, 4. Okay, so what this ends up being is this ends up being 0.0008 parts of carbon monoxide per 100 parts of air. Well, in other words, this comes out to 0.0008% carbon monoxide. Well, 0.0008% is kind of a hassle to say. And so it's much easier to say 8 ppm, right? And so just move the decimal over. But you see that 8 ppm carbon monoxide is exactly the same thing as 0.0008 parts per 100 carbon monoxide here. In other words, if I have 100 molecules of air, let's just take an air sample. I have 100 molecules of air, then it's likely I'm not even going to see 1 molecule of carbon monoxide. It's only when I get a sample of 1 million molecules of air, I take 1 million molecules of air and then I'm going to find 8 carbon monoxide molecules in that sample of 1 million. That's part per million. And so for things that are very low, these are more like contaminants rather than main components, but for things that have very low, what we call concentration, that the composition isn't so high, then we use this. We either use parts per million, we could even go parts per billion. And so what would this be in terms of parts per billion? Well, if we did this in parts per billion, what we'll do is we'll go first. We'll go with 8 molecules of carbon monoxide in 1 million molecules of air. And so if I take 1 million molecules of air, I'm going to see 8 molecules. Well, what happens if I take 1 billion molecules of air? If I take 1 billion molecules of air, how many molecules of carbon monoxide am I going to have max?
0.70.
Well, what did I do? I added 3, so I got to add 3 here. And so if I add 3 here, I add 3 here to get the same. And so if I had 1 billion air molecules, I'm going to find 8,000 carbon monoxide molecules. Well, that's 8,000 carbon monoxide molecules per billion, which means this is called 8,000 parts per billion. And so these are all the same thing. 0.0008% is the exact same thing as 8 ppm, which is the exact same thing as 8,000 ppb carbon monoxide. So which one do you use? You use the one that's easiest to say. The one that's easiest to say is parts per million. And so we stick with parts per million until we get to, let's say, if we go 100, 100 is easy to say. 150, 200, 300 is easy to say. When we get to 999, that's fine. But when we get to 1,000 parts per million, if we get to 1,000 parts per million, we might as well call that 1,000 parts per million is the same thing as 1 part per billion. And so we'd switch to, once we hit 1,000, we switch it to parts per billion. Once we get to 1,000 parts per billion, we'd switch it to parts per trillion. And so if we have 1,000 parts per billion, well, 1,000 parts per billion is exactly the same thing as 1 part per trillion. Does that make sense? Or am I going the wrong way? Maybe I'm going the wrong way. Yeah, I'm going the wrong way. 0.001. 0.001 is too much hassle. Well, anyway, do you get the point? Good enough? Okay.
I think what you meant was like, if it's like 1,000 parts per billion, you can just call it 1 part per billion.
Yes, that's what I meant to
You're
say.
going the right way on the wrong side.
Yeah. Let's go on the right. Okay, let me redo that. Then.
Go the right side, wrong direction.
Right. So if I had 1,000 parts per trillion, then I'd want to go that way. But I would probably start with this. If I have 80%, how about this? You know what? Maybe I don't want to do it. Maybe I want you to do it instead. Okay, 80% nitrogen is equal to how many parts per million nitrogen in air? And so 80%, this is by molecules, or volume, if you want to say, not weight. And so we have 80% nitrogen. How many parts per million nitrogen is that? And then how many parts per billion nitrogen is that? The first one, 80 million? 800,000?
Yeah.
Most people get 800,000? 800,000 is correct. There would be 800,000 parts per million nitrogen. What about parts per billion? 800 million. 800 million parts per billion. Well, that's a hassle to say. 800 million parts per billion was inconvenient. And even 800,000 parts per million is too much. So the easiest would just call it 80% parts per hundred. All right, so that's typically how we represent mixtures like this. But we don't have to do it by molecules. We can also do it by grams. And do you know air? If you weigh air, it doesn't come out to 80% nitrogen. It comes out to a different percentage because one, air is a very common mixture, so they get the average weight of air. The average weight of air depends on how much nitrogen, how much oxygen. You just take the average. It's a weighted average. And then nitrogen weighs a different amount than oxygen. So it's a little bit trickier, but it's okay because we're going to talk about weight percentages or mass percentages very soon. So if it's a mixture, we want to know the composition of the mixture and by percentage and by component, what substances are present. Now substance, a pure substance, what did we say a pure substance is? Pure substance is either an element or a compound. And so we want to see what elements and compounds it's made up of. Now, get to this question here. Now, what is this? Is this pure water? Well, no, because you saw me get it out of the tap, but if you didn't, how can you tell? How can you tell? You could taste it, but if there's poison in there...
I'm not sure, but I heard like pure water does not conduct electricity.
Pure water does not conduct electricity, that's correct. So one thing you could do is you could put what you call ohm meter in here and measure the resistance. Pure water should have mega ohm resistance, which is 1,000,000 ohms of resistance. But it's still, could be contaminants. There could be contaminants that do not conduct electricity. Minerals conduct electricity. There's a tap water, the electrical resistance there is a lot lower than pure water. And tap water conducts electricity quite well compared to pure water. So that's good. You can test its properties like that. It's electrical. Is there another way?
You find one.
Actually, let me tell you. Just one quick thing. That's very good about the electricity because that's normally how I checked our water. I had to use ultra pure water for some of my synthesis. They did at UCLA. So I'd wheel a cart. I don't know why they kept the stills in the psychology building, but they had the stills there. So I'd take a cart from the chemistry building to the psychology building and fill up my jugs full of water. And the water, the way they purified it is they distilled. First, they passed it through filters, that kind of stuff, and then they distilled it not once but twice. They doubly distilled it. It's called double D water, doubly distilled water. And then they hit it with UV, and then pass it through an ohm meter. So you just watch the ohm meter as you get the water and see. And so I was always looking for mega ohms. Well, anyway, the other thing, well, how can you tell this is pure? Well, it's the same kind of thing. How can you tell, pure gold from fool's gold?
It's the pH. I don't know. It's just
The pH? Yeah. Well, yeah. It's pretty easy to tell fool's gold from real gold, right? Because they have totally different properties, and so by looking at the properties, by measuring some of the properties, you can easily tell the difference. And there are lots of different properties to look at, and the more properties that we can use to confirm the identity of the substance, the better. The more confidence we have, because before I would drink this, I'd want to test a lot of things. Or, your water district probably tests it. Have you ever looked at the water analysis they send? The water district send a water analysis every year. In the water analysis, it's mostly, I don't think there are any percentages. Most of the components are in parts per million, parts per billion, parts per trillion. And so you can see how much chromium is in here in parts per million or parts per trillion, how much lead, how much whatever else is in there. Because they go through and they analyze for those types of things in your water. But we would look for the properties. Now, where are you going to find such properties? Such properties that we can use to identify substances, because one of the things is pure substances or substances have fixed composition and fixed properties. And so where do we see these things? Well, let me show you a couple of references. One of the big references is the CRC Handbook of Chemistry and Physics here. This is it. Let's just go to Amazon. Or actually, no, Wikipedia might be better. Let's go to Wikipedia. Take a look. These are yesterday's.
Professor, that reduction, is that anything related to microdots and microfish?
Well, microfiche is like kind of the shrinking down. No, it's not. It's different. Data reduction is data reduction. Does somebody have a good definition for data reduction? I'll show you some data. You want to see some data reduction?
Sure. No.
Since we're on this topic, let me just cover it.
Where's the shooting in Florida?
That's just what's going on here. Do you see all this data? This is not that much. This is only 49 entries. That's not that much data. Let's see if there's a bigger chart of data there. What's wrong with this here? Let me go to Chrome. I was having issues earlier. Here's some examples of data reduction right here. All right, this is actually a lot of entries. As we have this is the temperature, and this is something called the vapor pressure of water here, which we'll talk about later. But there's a temperature and vapor. In other words, as you heat up the water, more water molecules will vaporize into the gaseous state. When more water molecules vaporize into the gaseous state, it creates a higher water pressure in the gaseous state, and that's what this is measuring over here. And so it starts at 19.1 degrees C, 19.2, goes down to 22, 22.1, down to 25, from 25 to 25.1 to 28, from 28 to 31, and then it should continue all the way up to 100. And so it just continues. So there's a lot of entries here. And so one way you could reduce all this data is you could do this. You could graph it. And so you graph it, this is what it looks like. And so you graph it like that. Is that linear or non-linear? It's non-linear, so the higher the temperature, the greater it is. So it just exponentially increases. It's exponential. But you know, a graph takes up a lot of space, a table takes up a lot of space. You know, this, if you know about math, and if you have some calculus or something like that, or maybe you do this in algebra. Do you do nonlinear graphs in algebra? Like semi-log, maybe? You try semi-log plot or something like that, and get a linear. But if you know some math, what you could do is you could just take this, and you see this, and you try to fit it to a line here, and generate a mathematical equation. And so we take that data table, we make this graph, and then that graph is defined by this equation here. This is a mathematical equation. This is a very famous equation called the Clausius-Clapeyron equation. Actually, the Clausius-Clapeyron equation we're actually going to do, I think, in this. Yeah, I'm pretty sure we do the Clausius-Clapeyron equation. If not here, for sure in Chem 1A, you do the Clausius-Clapeyron equation. The Clausius-Clapeyron equation just says the y, you know, this is the y is equal to, it's equal to some constants, you know, this is something called minus delta H, so dAq over R, 1 over T2 minus 1 over T1. And so the X is the temperature. This is X2, this is X1. And so what we can do is we could just take all that data and just say, okay, this is it. Now if I have this equation, give me any temperature. Any temperature, I'll tell you what the Y is going to be. You know? And that sure beats doing this. That beats going to a table like this. If you have a table like this, the way, this is what I used to do in algebra when we had logs, when we didn't use calculator. We had to do this by hand. We do interpolation. So this is 60 to 65 degrees C. Well, if I had 63 degrees C, then I don't have a data point. And so what I do is I have to assume it's linear between 60 and 65, which it isn't. But I assume it's linear and then do a linear interpolation. Have you ever done linear interpolations? Or, you know, if it's beyond the table, you do a linear extrapolation where you just say, okay, it's still going to shoot out as a straight line, and we'll just predict where it's going to be, you know, further down the road. That's analyzing tables, which we're going to do. Actually, we're going to do that next week in lab. We're going to do linear interpolation and linear extrapolation in lab, because this is a common technique that's used in lab. But you know, the other technique, and this is also what we're going to do, is give me a temperature, I'll figure it out. I'll draw off the graph, you tell me the temperature, I'll mark it here, and then go out and figure out what my y is by using a ruler. If I want to extrapolate, I'll just imagine this line continuing, and I'll just extrapolate it out, and I'll just say, okay, I use here, and then guess what's going to be there. That's it. You use a graph. The graph and data table take up a lot of space, don't they? So what's much easier is to, and this is the most concise definition of that data table, and the most concise definition of the graph is the mathematical equation. Mathematical equation is the most concise, most compact definition of this. That's called data reduction. If you take all that tremendous amount of data and reduce it into a simple equation like this we call what do we call this? This is called an empirical equation. This equation is based on observations, and this equation would be called a law. This is a law. It doesn't tell me why, it just tells me the pattern. That's all, the trend. Well, okay, well, it's time for a break, so let's take a break for